Zero order reaction. Well, I will teach you the complete concept of zero order reaction and its numerical problems. Now, what is zero order reaction? A chemical reaction in which the rate is independent of the concentration of the reactants is called zero order reaction. For example, consider this general reaction. According to rate law, the rate of this reaction is R is equal to K into concentration of a reactant raised to the power 0. Or we get R is equal to K. It means that rate of zero order reaction purely depends on rate constant K. If we increase the concentration of a reactant, the rate of zero order reaction remains the same. Similarly, if we decrease the concentration of a reactant, the rate of zero order reaction remains the same. I mean, increasing or decreasing doesn't affect the rate of a reaction. It only depends on rate constant or velocity constant K. In chemistry, the best example of zero order reaction is photochemical reaction. For example, in the presence of suitable photons, hydrogen gas and chlorine gas is converted to hydrochloric acid. Experimentally, the rate of this reaction is R is equal to K. It means that this is zero order reaction. Even if we increase or decrease the concentration of hydrogen gas or chlorine gas, it doesn't affect the rate of reaction and it remains constant. Thus, we learn that zero order reactions are those reactions whose rate of reaction doesn't depend on concentration of the reactants. Rather, the rate of reaction depends only on rate constant K. Hence, note down these important points. Now, you must learn 3 important graphs of zero order reaction. For example, consider this general reaction. Here, the reactant is A. Let I take 100 molecules of A per liter. Now listen carefully. As the time passes, the concentration of A decreases and product is formed. Let me repeat it. As the time passes, the concentration of A decreases and product is formed. Thus we learn that concentration of A reactant decreases with respect to time because it is converted to product. Now let me ask you, draw a graph for the concentration of A reactant against time. Can you draw it? Well, it is super easy. I draw 2 perpendicular lines. Along x-axis, I take time t. Along y-axis, I take concentration of A reactant. We know that the concentration of A reactant decreases with the passage of time. So I draw this decreasing line. This line shows that the concentration of A reactant decreases with respect to time. Now what about its slope? We know that the angle theta is always formed at x-axis. This is angle theta. The slope of this line is tan theta or minus K. Thus this is the graph of concentration of A reactant against time. Secondly, let me draw a graph of rate of zero order reaction against concentration. I draw 2 perpendicular lines. Along x-axis, I take concentration of the A reactant. Along y-axis, I take rate R of the zero order reaction. We already learned that rate of zero order reaction doesn't depend on the concentration of the A reactant. So I draw this straight line parallel to x-axis. This line shows that the rate of reaction remains constant even if we increase or decrease the concentration of A reactant. Thus, this is the graph of rate of zero order reaction against the concentration of the reactant. Thirdly, let me draw a graph of rate of zero order reaction against time t. As usual, I draw two perpendicular lines. Along x-axis, I take time. Along y-axis, I take rate r of the zero order reaction. Now listen carefully. We know that the rate r of zero order reaction remains constant. I mean, if it is 5 mole per liter per second, then at any time it will remain 5 mole per liter per second. It will never change. So I draw this straight line parallel to x-axis. It means that the rate of zero order reaction remains constant. Thus this is the graph of rate of zero order reaction against time. Hence noted down these three important graphs. Now let me teach you integrated rate law for zero order reaction. Let's consider this general reaction. Let at time t is equal to 0 second, the initial concentration of the A reactant is A0. Usually it is considered as 100. So whenever you see A0, this naught will remind you initial concentration of the A reactant. One can also say that T is the initial time and A0 is the initial concentration. Now after some time, T1 is equal to T, the initial concentration of the A reactant decreases to A. I mean, this T is after 5 seconds. The initial concentration decreases from 100 to 60. So T1 is the final time and this A is the final concentration of the A reactant. I am interested to write a rate of reaction for this zero order reaction. We already learned in our previous lecture that there are two methods to write a rate of a reaction. One is differential method and the second one is rate law expression. In the differential method, we write rate of the zero order reaction is equal to minus dN to concentration of A upon dt. Let this is equation number 1. While in the rate law expression, we write R of the zero order reaction is equal to K because it is a zero order reaction and its rate doesn't depend on concentration of reactants. Let this is equation number 2. Now comparing equation number 1 and equation number 2, I write minus d into concentration of A reactant upon dt is equal to K. I shift dt from the left hand side to the right hand side. I also shift minus sign from the left hand side to the right hand side. I get d into concentration of A reactant is equal to minus K dt. Now listen carefully. This d represents differential and this d also represents differential. Note it down that if you want to cancel d or differential on both sides, you need to take integral on both sides. Let me repeat it. If you want to cancel d or differential on both sides, you need to take integral on both sides. For example, I have d is equal to d. Now to cancel these two, we take integral on both sides. As a result, this integral and d cancel out, this integral and d cancel out. Thus remember that to cancel d on both sides, we get integral on both sides. I take integral on both sides. I get this result. Here, this rate constant K has a fixed value. The rule of integration is to write all constant outside it. I write integral d into concentration of A equals to minus K integral dt. We know that the concentration of A reactant changes from initial value A0 to final value A. I write the initial value of concentration A0 here and I write the final value of concentration A here. Similarly, the time also changes. I write the initial value of time is 0 and the final value of time is t. According to the rule, this integral and d cancel out. This integral and d cancel out. I write concentration of the A reactant. The lower value or the initial value is A0. The upper value or the final value is A is equal to minus K, and to the lower value or initial value of time is 0. The upper value or the final value of time is t. Here, the rule for lower and upper value is upper minus lower. I write the upper value, which is A, minus the lower value, which is A0, is equal to minus K. The upper value of time is t minus the lower value of time is 0. Or I write A is equal to A0 equal to minus KT. I shift A0 from the left hand side to the right hand side. I get A equals A0 minus KT. This is known as integrated rate law for zero order reaction. We know that A0 is the initial concentration of the A reactant, which is usually considered as 100. A is the concentration of A reactant at particular time. K is the rate constant or velocity constant. T is the time in which concentration changes from A0 to A. Thus noted down this integrated rate law for zero order reaction, which we will use to crack any numerical problem. Now we will learn half-life of zero order reaction. Well, the time taken for the reactant concentration to react half of its initial value is called half-life. For example, consider this general reaction. Let the initial concentration of the A reactant is A0 or 100. After time T is equal to 2 hours, let 50 molecules of the A reactant is consumed or converted to product. This 50 is half of the 100, our initial value. I write here A0. Now listen carefully. This 2R is called half-life of zero order reaction because in 2 hours, half of the reactant is consumed or converted to product. Let me repeat it. This 2R is called half-life of zero order reaction because in 2 hours, half of the reactant is consumed or converted to product. Thus remember that half-life is the time in which 50% reactant is converted to product. Now at time is equal to 0, let the initial concentration of A reactant is A0. Let at half-life, the concentration of A0 is 50% consumed, so it is A0 by 2. According to the integrated rate law, A equals to A0 minus KT. We know that this A is the final concentration. Here, the final concentration is A0 by 2. I write A0 by 2 equals to A0 minus K. The time is half-life or T1 by 2. I write T1 by 2. Now I shift minus K and T from the right hand side to the left hand side. While I shift A0 by 2 from the left hand side to the right hand side, I get K into half-life is equal to A0 minus A0 by 2. Or I get K into half-life is equal to A0 by 2. Here, I shift K to the right hand side. I get half-life is equal to A0 by 2K. This is the equation of half-life of zero order reaction. You must memorize it because we will use it to crack zero order numerical problems. Now we will start the numerical part of this lecture. Firstly, we will learn type 1 numerical problems. These types of numerical problems are super easy. We are given the data in the numerical problem and we will just put the data in the integrated rate law. For example, consider this numerical problem. How long will it take for the initial concentration of A to fall from 0.3 m to 0.01 m if K for a zero order reaction is 0.005 mole per liter per second? Well, I write the given data. The initial concentration A0 is 0.3 m. The final concentration A is 0.01 m. The value of rate constant is 0.005 mole per liter per second. The time t is unknown. According to the integrated rate law expression, A equals A0 minus Kt. Now I shift minus Kt from the right hand side to the left hand side. And I shift A from the left hand side to the right hand side. I get Kt is equal to A0 minus A. Or T is equal to A0 minus A upon K. Now I plug in all these values in this equation. I write T equals to 0.3 minus 0.01 upon 0.005. After calculation, I get 58 seconds. So the time is 58 seconds. It means that in 58 seconds, the concentration of A reactant will drop from 0.3 m to 0.01 m. Thus, using this integrated rate law, you can easily crack type 1 numerical problems. Now we will learn type 2 numerical problems. In this type of numerical problems, we are given two types of percentage. Firstly, I will solve it for board exam and then I will teach you my personal trick to crack it in less than a minute. For example, consider this numerical problem. The reaction is a zero order reaction. If time taken for 50% completion is 2 minutes, find the time required for 43.33% completion of the reaction. Well, in such type of numerical problems, I always write two equations. Let's consider that the initial concentration of A reactant A0 is 100. After time t is equal to 2 minutes, the concentration decreases 50%. I write A equals to 100 minus 50 is equal to 50. It means that after 2 minutes, 50% concentration of A reactant is used and 50% concentration of A reactant is remaining. Now according to integrated rate law, I write A equals A0 minus Kt. Here, I shift minus Kt from the right hand side to the left hand side and I shift A from the left hand side to the right hand side. I get Kt is equal to A0 minus A, or K is equal to A0 minus A upon T. I put these values in equation number 1. After calculation, I get K is equal to 25. Let this is equation number 1. Similarly, we are asked to find the time. I write time is equal to unknown. For 43.33% completion of reactant, let the initial concentration of A is A0 and it is equal to 100. I write A is equal to 100 minus 43.33%, which is equal to 56.67. It means that 43.33% concentration of the A reactant is used and the remaining or final concentration is A, which is equal to 56.67. Now according to the first equation, K is equal to 25. I write the integrated rate law. A is equal to A naught minus KT. After rearranging, I get T is equal to A naught minus A upon K. I plug in all these values in this equation. After calculation, I get T is equal to 1.73 minute. So the time is 1.73 minute. It means that the reaction will take 1.73 minute to be 43.33% completed. Now I will teach you my personal trick to crack this type of numerical problems in less than a minute. I write 50% reaction takes 2 minutes to complete. Then 43.33% reaction takes X time to complete. Now I cross multiply them. I get 50x is equal to 2 into 43.33. I shift this 50 from the left hand side to the right hand side. I get this result. After calculation, I get x is equal to 1.73 minute. Thus after 1.73 minute, 43.33% of reaction is completed. Therefore, using my personal trick, you can easily crack type 2 numerical problems in less than a minute. Now we will learn type 3 numerical problems or JEE main MCQs. In such type of numerical problems, we use both the equations, equation of half-life and integrated rate law expression. For example, consider this JEE main MCQs question. According to the given statement, the initial concentration of the X is 0.2 m and the half-life is 6 hours. I write initial concentration A naught is equal to 0.2 m and the half-life T1 by 2 is equal to 6 hours. The value of K is unknown. According to the half-life equation, half-life is equal to A naught upon 2K. I plug in all these values in this equation. I get 6 is equal to 0.2 upon 2K, or K is equal to 0.0166. This is the value of K for this reaction. Secondly, according to the given statement, when the initial concentration of X is 0.5 m, the time required to reach its final concentration of 0.2 m will be dash. I write A naught is equal to 0.5 m. The final concentration or A is equal to 0.2 m. The time T is unknown. We have already calculated that K is equal to 0.0166. Now according to integrated rate law, A is equal to A naught minus KT, or T is equal to A naught minus A upon K. I plug in all these values in this equation. After calculation, I get T is equal to 18 hours. So the time is 18 hours. Thus B is the correct option. Therefore, using this method, we can crack any numerical problem of zero order reaction.